I would like to thank the organizers and OGT for allowing me to present our lab's work on transitioning CLL FISH analysis into the molecular biomarker era using the OGT NGS CLL panel. Our lab has the following disclosures. I have not received any personal compensation from OGT for this presentation. The outline of today's talk, I will cover first our current approach to CLL testing and a brief summary of the OGT CLL NGS panel content and the limit of detection. I will present results of the initial proof of concept analysis, including the CNV, SNV, and prognosis comparison of FISH and NGS, as well as the future directions that we're going to take with the OGT panel. Within the province of British Columbia, we are one of 4 labs that provide CLL FISH testing. We perform approximately 200 CLL FISH cases per year, or about 4 per week. We use a 2-probe set analysis, and each of our technologists count 100 nuclei each for each of the probe sets. The first probe set is a dual color probe set that consists of 11Q and 17P, and we have a tricolor probe set that will assess for trisomy 12 and deletions of 13Q. Depending on the probe set, our current cutoffs range from 7 to 9%, which would correlate to a variant allele frequency of 3 to 5%. Our preferred specimen for FISH analysis is a peripheral blood. Typically, we perform a direct harvest on the peripheral blood once it arrives in the lab, but if it arrives late in the day or after 3 p.m., we do culture it overnight. Currently within the province of British Columbia, TP53 sequencing is not routinely offered to CLL patients, which means that we're missing a proportion of patients who have a TP53 mutation without a corresponding 17p deletion, which could affect patient management. Our lab does offer a larger NGS panel for myeloid malignancies that does cover TP53, but it's not an economical option for CLL patients. Furthermore, having an NGS platform to detect sequence changes and FISH analysis to detect copy number analysis does not provide a streamlined option. By having an NGS platform that could perform both copy number and sequence analysis would allow us to unify our workflow in the lab. We also have the capability of performing the 200 FISH tests per year by an NGS, as we have an automated nucleic extraction as well as liquid handlers for both our pre and post PCR. Because we work within a public healthcare system and our lab also works from a global budget, we need to assess similarly cost assays to replace our current FISH platform. The CLL NGS panel is a hybrid capture-based NGS panel. It has 14 genes where you can detect SNVs or indels with a detection limit of greater than 1% VAF. There are 5 loci that are looked at for somatic CNV callings. As I said on our previous slide, we do not look at 6Q deletions, nor did we find any within this proof of concept. The estimated tumor content that is detected by this assay is said to be 20% or a VAF of 10%. We performed a proof of concept analysis using the OGT NGS panel. We began by generating a normal reference set, which consisted of 20 DNA samples from patients who had an indication other than CLL, who had been tested and found to be normal using a different and larger targeted NGS panel and copy number analysis. This reference set was obtained over 2 NGS runs. We included 20 CLL patients who were previously characterized using FISH, and 2 samples were run in duplicate over 2 separate NGS runs. The peripheral blood was collected in sodium hep for FISH and in EDTA for NGS. We ran 16 samples at a time on an aluminum mini-seq using a high output flow cell. This is a summary of our results thus far. We had 3 patients with a 17p deletion, and the abnormal nuclei that were estimated by FISH ranged from 56 to 81%. We had 5 patients who had an 11q deletion with a tumor percent of abnormal nuclei by FISH ranging from 24 to 87. We had 3 patients with trisomy 12 and abnormal by FISH of 43 to 76%. And we had a number of patients with 13q deletions. We had 9 with only a heterozygous deletion identified by FISH, and the abnormal nuclei range between 29 and 91%. 1 homozygous deletion that was identified at 84%, and 4 patients who had heterozygous homozygous deletions that had an estimated abnormal nuclei ranging from 16 to 85%. When we looked at the NGS calls, the software actually provides an estimated tumor content, which is in brackets below. We had the 3 patients that had the 17p deletion were also identified by the NGS platform with an estimated tumor content of 56 to 70%, so very similar to the abnormal nuclei that we identified by FISH. 3 of the 5 patients who had a 11q deletion were identified by the NGS platform. The NGS platform missed 2 patients who had abnormal nuclei of 24 and 28% by FISH. Both of these cases were actually run in duplicate on 2 separate runs and were negative both times. All 3 patients with trisomy 12 were identified with an estimated tumor content of 47 to 67%. The 12 of the 14 patients who had a 13q deletion were identified by the NGS platform. The NGS platform did miss a case with the 16% abnormal nuclei, and this had a combination of both a heterozygous and homozygous. This is considered discordant by design, as it is below the stated limit of detection by the company. There was a case with 35% abnormal nuclei by FISH that was not identified by the NGS platform. The double asterisk here is indicating that we had 1 case of a 13q deletion that was not called by the software, but upon visual inspection was identified. And it's shown in the slide next. This is the output for a patient who had the 13q heterozygous deletion identified in 29% of FISH nuclei. Although the software did not call this as a deletion, on visual inspection you can clearly see that the log2 ratio has shifted down below the 0, that I would be confident in calling this as a deletion in this patient. Similarly, this is the output for 2 patients who had an 11q deletion. The top one identified in 28% of nuclei by FISH, and the bottom identified in 24% of nuclei by FISH. In both of these cases, the NGS platform did not identify the deletion, and you can see, unlike the 13q deletion, I don't see any clear shift in the log2 ratio that would hint that there is a deletion in either of these patients. We often see patients with both heterozygous and homozygous deletions of 13q by FISH. This is one patient who we identified only a homozygous deletion by FISH in 84% of nuclei. And when we look at the output from the NGS platform, we can see on the left that there is a small region that shows a heterozygous deletion, or what we would suspect is a heterozygous deletion, in a smaller subclone relative to the larger population with the 84% deletion that was detected by FISH. And if we look at where the FISH probe sits, it does not cover the RB1 locus, in which is where the heterozygous deletion was identified. So the NGS platform helped us to identify a heterozygous subclone that was in this patient. It may be possible to distinguish patients who have homozygous or heterozygous, or a combination of both the heterozygous and homozygous deletions by the NGS platform. The first patient here is the one that I showed on the previous slide. If we look at the log2 ratio, the heterozygous deletion that was identified in this first patient, that's shown on the left, had a log2 ratio of minus 0.62, where the homozygous deletion in the same patient, shown on the right, had a log2 ratio of minus 3.9. In the middle panel, in patient 2, who had a heterozygous deletion of 13q identified in 70% by FISH, had a log2 ratio of minus 0.44. In the final panel at the bottom, patient 3 had a heterozygous deletion identified in 38% of nuclei by FISH, and in 45% of nuclei there was a homozygous deletion. And if we look at the log2 ratio of this patient, they had minus 0.99. Now this is a small sample set, but it may be possible with future analyses to distinguish patients who have a heterozygous and homozygous deletion and distinguish them from patients who have either just a single heterozygous deletion or a homozygous deletion. We ran 2 patients in duplicate, and this is showing the output from one of those patients who had a heterozygous deletion of TP53 identified in 56% of nuclei by FISH. This patient was run in duplicate in 2 separate NGS runs, and in both instances, the tumor content estimate by the NGS platform was 57%, which shows good correlation with the FISH analysis. And this may be important as there is growing evidence to suggest that the percentage of abnormal nuclei by FISH may play a role in prognosis, indicating that the tumor content that's estimated by NGS serves as a good surrogate for the FISH. With this in mind, we also wanted to look at whether there was an effect of culturing the peripheral blood and the percentage of abnormal nuclei that we identified by FISH versus the tumor content estimate by NGS. Looking at this graph, we have the black dots indicating specimens that were a direct preparation, and the blue dots represent those that were cultured. And on the x-axis, we have the abnormal nuclei by FISH, and the y-axis shows the percent tumor content by NGS. And we can see that there is not a strong bias when the sample is cultured relative to the tumor estimate by NGS, which is a good indication for our lab because we have to perform both direct preparations and cultures for our specimens. So looking at the SNVs that were identified in the patients, we at most identified 3 mutations per patient. There were 6 patients who had no mutations identified. There were 10 patients who only had a single SNV that was identified. And if we break it into the number that had variants of unknown significance versus those with known functional significance, there was 2 patients who had an ATM mutation that was considered a VUS by the lab. There were single changes identified in 1 patient with KRAS, 2 patients with TP53, 1 recurrent Notch1 mutation that was identified. 2 patients had frame shifts in MIB. There was 1 patient who had an MYD88 frame shift, and 1 patient with an inactivating BRCA3 mutation. 2 patients had 2 mutations each. 1 of those patients had an SF3B1 mutation that was considered a VUS. 1 recurrent Notch1 mutation was identified, an inactivating XPO1, and 1 patient with a BRCA3. 3 mutations were identified in 2 patients. There was a patient with 3 low-level ATM mutations that were considered a VUS, and the VAFs range from 1 to 2%, and the hypothesis is that this, rather than represent something that's relevant to CLL, could be an indication of CHIP in this patient. We also identified in another patient a TP53 mutation that was considered a VUS. We identified 1 XPO and 1 BRCA3 mutation in 1 patient. We wanted to compare the prognosis that's provided by FISH to that of the NGS calls. Overall, we had 9 patients who had a good prognosis by FISH who had 13 Q deletions. We had 5 patients who had an intermediate prognosis with either a normal FISH pattern or trisomy 12, and 6 patients who had a poor prognosis either from having an ATM or TP53 deletion. After performing the NGS, 4 of the 6 patients who had a poor prognosis were given a poor prognosis by the NGS panel CNV analysis. As shown, there was 2 patients with ATM deletions who had abnormal nuclei of 24 and 28%, which were identified by FISH, that was not identified by the NGS platform. These patients also had 13Q deletions identified by FISH and NGS and were subsequently downgraded in their prognosis because of missing the ATM deletion. So they went from having a poor prognosis by FISH to having a good prognosis by the NGS platform. We had 7 patients after the NGS that had an intermediate prognosis. These included 2 patients who had a good prognosis by FISH by the identification of a 13Q deletion. Both of these 13Q deletions in these 2 patients were missed and thus looked to have a normal CNV pattern and were classified as having an intermediate prognosis. So these 2 patients were given a higher grade prognosis than they were by FISH. We had the 9 patients that had a good prognosis were identified by CNV analysis, but again, this is not the same 9 that were included by FISH analysis. If we incorporate the SNVs that were identified by sequencing, there weren't any new changes that would change the prognosis in these patients. We did identify 2 TP53 mutations in patients who already had a corresponding CNV within TP53, indicating that these patients were compound hets for inactivation of TP53. So far, we have been impressed with the results that we have obtained using the CLL OGT NGS panel. There are a number of studies that we would like to perform to see if we could catch those cases that were not identified by the NGS platform. We're going to start by determining what our in-house limited detection is, and we're going to do this by performing a dilution series. Because of the complication of using peripheral blood that is both a myeloid and lymphoid fraction, we are going to obtain a peripheral blood specimen from a patient with known CNVs with CLL, and we are going to fractionate the peripheral blood into myeloid and lymphoid fractions. We'll then use the DNA extracted from the myeloid fraction to dilute the lymphoid fraction to determine our limit of detection. We also want to look to see if we can lower the threshold for the software to call CNVs. Obviously, we want to do this without increasing our false positive rate. We'll look to verify any of our false positives that we obtain by lowering the CNV calling by digital droplet. We're also going to look at our normal reference set that we created from the 20 peripheral blood specimens to see if we can substitute any of those, which could increase our detection limit for the assay and could be contributing to the false negatives that we see. So with these future directions, we hope that we would be able to increase the number of patients with known CNVs that could be detected by the NGS platform.